Today we're going to be talking about different field and laboratory tests that can be performed on parking garages during a parking garage evaluation. These are not necessarily unique to parking garages. They can be done on pretty much any concrete structure, certainly any exterior concrete structure in particular. A couple of ground rules we should go over. As Lindsay mentioned, submitting any comments or questions via the chat feature. We can address those at the end of the presentation. 100% participation is required to receive credit. Submit answers when prompted. Lindsay mentioned that they're timed. 45 seconds seems like a long time, but everyone should have plenty of time to weigh in. One thing I do want to mention, if you're in a larger room, maybe a conference room where you've got multiple people in listening, listening, only the individual that signed up for the seminar is going to get credit. So if you've got multiple people in a room, only one of those people may get credit. So just a brief outline, we'll talk a little bit about planning an investigation evaluation. We'll talk about different field evaluation methods, ground penetrating radar, ultrasonic testing, impact echo, handful of others. Then we'll have a learning assessment in between the field and laboratory discussion, and then we'll have a laboratory discussion about some different test methods that are typically done in a laboratory on samples that are brought in from the field. And then we'll have a learning assessment at the very end after that as well. So planning a field investigation, some of this may seem fairly basic, but if you got project plans, definitely have them available, request them from the owner. Sometimes they can be gotten from municipal records. Always be sure to take lots of notes, lots of good photos. I can remember years ago, the time of non-digital cameras, analog cameras, 35 millimeter film. You might take 20 or 30 pictures. Nowadays, it's not uncommon for me or others to take dozens or hundreds of pictures in a day. Pictures are cheap. Take lots of pictures. Make sure you take good notes so you understand what you're taking pictures of. A lot of us that do field work, maybe it's 4 or 5 days or maybe a couple of weeks before we get back to the office and start writing up our reports. It's always uncomfortable when you get to a picture and you ask yourself, what is this? What am I looking at? Why did I take this picture? That's why it's important to make sure you got good notes. Use standard terminology. ACI 201.1 is a really good document. It's got a lot of definitions. It's got a lot of pictures that go along with the definitions. All of those definitions, those are, it's just good to have good definitions so that we're all using the same terminology, the same words, things like that. Things aren't being confused. Make sure you understand why you're out there, what you're doing. The purpose of your investigation may change as you get a little bit more information and go out there. Maybe you think you're going in one direction when you got boots on the ground and 15, 20 minutes or a couple hours into the investigation, you realize things aren't what you thought they were going to be, and maybe you got to change gears, which is why you should always keep an open mind throughout the investigation. So all these pictures here, I took of various different parking structures. 4 out of 5 have one thing in common, other than concrete. They've all got signs of, corroding, rusting, reinforcing steel. That's certainly one of the more prevalent issues that we see in parking structures, exposed to freeze-thaw, de-icing chemicals, things like that. The picture in the middle I put in because I mentioned in the last slide, keeping an open mind. There was an engineer I was working with that came out to this particular parking garage, saw this pedestal or whatever, and kind of the map crack pattern on here, and he's like, "Oh, this is ASR. This whole thing's got ASR. That's the problem. We're looking at ASR." We took some cores, we did some petrographic analysis on the cores. We didn't find ASR anywhere, and what we're looking at there are really just superficial crazing cracks, which are usually not very deep. Maybe a 1/16 of an inch, a 32nd of an inch, sometimes not even that deep. But my point here is, make sure you keep an open mind, and things aren't always as they appear to be on the surface. So we'll get into some different field evaluation methods. Ground penetrating radar. Most people are familiar with this. It's a great tool for locating embedded items such as reinforcement tendons. A lot of parking garages have got pre-stressed tendons. And in some of the beams and girders, you can see voids, anomalies. Sometimes you can get thickness, under the right conditions, the thickness of a slab or something like that. It is very versatile, but it definitely has some limitations, and I always like to discuss those limitations with our clients. You can't get bar size with GPR. I don't know of a GPR instrument on the market that'll give you bar size. There are other instruments that'll give you bar size, but right now I'm not familiar with any GPR that'll give you bar size, unfortunately. Anomalies, although sometimes they show up really well, sometimes they're not always evident. There's different settings you can change on a GPR to maybe make some of those stick out a little bit better. A lot of this really comes down to the operator and the experience of the operator, understanding what they're seeing. Definitely a primary tool that we use for all types of concrete investigative services to kind of help you see inside the concrete. But it's not like an X-ray, where if you take an X-ray of your hand, you can obviously pick out 4 fingers and a thumb. Whereas GPR, that's not necessarily the case. You're looking at the data a little bit differently. So here we've got kind of an image of a GPR scanning along the surface. Most of the concrete GPRs are about the size of a shoebox or so. And for the reinforcement, you get these kind of parabolic reflections that we see down here at the bottom. And that parabolic shape is really due to the function of where the GPR is relative to what this cylindrical target is. Essentially, it's a rebar. We traverse at a perpendicular angle across the reinforcement, and we get these parabolic patterns. The tails before the peak and the tails after the peak are just a function of the distance between the antenna and the target. So if you look here at the top, here we've got a distance D1, that's kind of this, beginning part of the tail. D2, where the peak of the parabola, that's where your antenna position is pretty much right over your target. It's the closest distance to the target. And then as you trail away from the target, the distance obviously gets greater, and you get this tail. When you add a whole bunch of them up together, you get a record that looks like this, where you've got multiple parabolas, showing or indicating, different pieces of rebar. Think of this kind of as an elevation view, where across the top is the like the x-axis is distance across the slab. This particular one is in inches, and then the vertical scale or y-axis is depth within the slab, also in inches. We can see we get a really strong reflection, or relatively strong high amplitude reflection at the bottom of the slab, which I've got identified here. So here we got about a 12-inch slab. The peak of these parabolas is that's where the reinforcement is. The depth to the peak, the distance to the peak, that's essentially your concrete cover. and then your peak-to-peak distance between parabolas is essentially your rebar spacing, which here is about 10 inches or so. So we get a lot of good information from this. Again, it's not like an X-ray. You're not seeing 4 fingers and a thumb. My guess is this is probably an elevated slab. Also, we're seeing some kind of remnant artifact reflections down here. If this was a slab on grade, you probably wouldn't see these. These would be just more noisy, for lack of a better term. But these are not peaks of a parabola, so there's not another layer of reinforcement down here. Again, that's where operator experience comes into play. Next method we'll talk about is ultrasonic pulse velocity. It's a standardized test method, ASTM C597. We've got a ultrasonic high frequency transmitter, typically right around 50 kilohertz, 54 kilohertz, and we're measuring the travel time of an ultrasonic pulse over a known distance. It's great for testing uniformity of concrete. We can delineate sound versus unsound concrete, damaged concrete, in piers, walls, columns, and it's great when both sides are accessible. So here's kind of the setup where you've got a transmitter or a source on one side. Think of this as maybe a foundation wall or something. You've got a receiver on the other side. You can physically measure the distance, so you know what the distance across here is. What the instant that pulse is transmitted and the instant it's received. You just take that time divided by the distance, and you get a velocity. If you've got any kind of voids or discontinuities or something inside the concrete that's going to impede the path, maybe slow down the wave path, then the signal is going to have a longer travel path from one side to the other, which is going to drive your velocity down, so you'll have a decreased velocity. So if you've got deteriorated concrete, you've got a cracked concrete, voided concrete, unconsolidated concrete, those pathways are going to be, they're not going to be a direct pathway from one side to the other. That pathway is going to increase, and again, that's going to decrease your overall velocity. We typically have 3 configurations that we do ultrasonic testing. This configuration is ideal where you've got access to both sides. This is considered a direct measurement. If you don't have access to both sides, maybe you've got access to adjacent sides like this. This is considered semi-direct. You can see that there's still kind of a somewhat direct pathway, although it's not direct, like from one face across to the other. And then the third configuration is an indirect, where you've got the transmitter and receiver both on the same surface. There are some benefits to testing in this indirect method, but it's not used very often. You can sometimes get crack depth using the indirect method. You can get some superficial concrete information, some information on the surface or the near surface. Say if there's fire damaged concrete or something like that, it can give you some information. But usually this direct method is most preferred. So here we've got a couple of piers we did some ultrasonic testing on. You can see this pier on the right, actually the one on the left also. You can see cracks here. You can see a crack up here, both of these towards the top. And we did our testing starting at the top, and we went down. We did about every 6 inches or so. We did see decreased velocities up here at the top because of this damage, because of this cracked pier. As we got below the crack, about 6 inches below the crack, everything was pretty uniform as far as the velocities went further down. So we did get some slower wave velocities up here, which we kind of figured we would get, but we wanted to see, how far down were those decreased velocities. So this was a really good tool to kind of help evaluate, where these cracks ended, really to kind of help come up with a repair method. So here's a unique situation we came across also on the same project. Design drawings showed a square pier right here. We get out to the field, and obviously this is not square. This was kind of I call it a field modified pier. Obviously the concrete's different. The corner of this pier was chamfered right here, so it was obviously formed up separately. We did ultrasonic testing from the right face of this pier to the other face of this field modification here. Up towards the top, we got really good signals from one side to the next, but starting at about 2 feet down, we weren't receiving any signals on the other side. So we basically came to the conclusion that this left portion of the pier was not in intimate contact with the right portion of the pier. This shadow that you see here is not although there is a physical gap that we were able to detect. This is just not in the same plane, so it's kind of casting a shadow is what you're seeing right there. But this was really good at being able to tell us again, that this modified portion just wasn't in intimate contact with this original portion. Never did figure out what the purpose of that modification was. Impact echo is the next method we'll talk about. It's great at detecting flaws. The depth of the flaw can be determined. Ultrasonic, if there are any flaws, ultrasonic doesn't tell you what the depth of that flaw is. Any kind of debonding or delamination of overlays, impact echo is pretty good at detecting that. Data processing can be kind of difficult. Interpretation can be kind of tricky if you're not really familiar with the method and understanding the method. Using terms like frequency domain and fast Fourier transform, amplitude spectrums we're looking at. It can be a little daunting to process and to understand. Impact echo is really mostly used in flat plate-like structures like slabs, walls, things like that. And that's because of the possibility of multiple reflecting surfaces. If you've got, like say on one of those piers, for instance, if we were to do impact echo, the 3 sides, so we've got 4 sides to the pier. One side we're using to impact. All those other 3 sides are going to reflect that impact signal. So those multiple reflecting surfaces can really make it difficult to interpret on anything other than a flat, kind of a flat plate, like we see here, which is kind of like it's kind of a slab. Again, it could be used on a wall also. But basically, you've got this small impactor that creates a stress wave into the concrete, and we're measuring the reflections off of either the backside of the concrete, the bottom of the slab, the other side of the wall, or maybe some of these internal flaws, or maybe if there's a delamination, in the upper region of the slab, we'll get a reflection off of that delamination. This is what typical data would look like. With impact echo, you get a dominant resonating frequency because it's bouncing back and forth off of either that flaw at the same location, maybe the bottom of the slab, the opposite side of the wall. So you get an echo reflection, at a specific frequency that just kind of goes back and forth within the concrete. So this is kind of what the raw data looks like. And here we've got this in the time domain. So you can see we've got a pretty regular repeating frequency up here. The amplitude's going up and down a little bit, but the frequency is pretty regular. When we process this, doing fast Fourier transformation and plot it in the frequency domain, here we see we get a dominant frequency at about 12.7 kilohertz, which, based on the wave speed within the concrete, that reflecting surface was about 7 inches down from the surface. So this is great impact echo data. We don't always get to see data that looks this nice. Sometimes we see data that looks like this, where we don't have a dominant resonating frequency. Here we've got, multiple dominant peaks. Most of these may be in the 20 hertz. These are 20 kilohertz range. But you can see there's no single dominant frequency. This is pretty typical of voided concrete, concrete that's poorly consolidated, honeycombed, stuff like that. So, although the data is difficult to interpret, it's still telling us something. So we can figure out the depth of the flaw using impact echo with this relatively simple formula. CP is the wave speed divided by twice of the resonating frequency. Again, we're doing twice the frequency because we've got it's going, we've got a path to the flaw and then a path from the flaw. So that's why we're doubling the frequency. This was a spot tested with impact echo. The delaminations ranged in depth from about 1 to 2 inches in this area right here. 1 inch is about as thin as you can, it's about a shallow flaw that you can detect with impact echo. There are some other impact echo equipment that can detect at less than 1 inch. But usually about one inch is about the minimum. GPR, by the way, ground penetrating radar, can be pretty effective at evaluating delaminations also. Here's a case where we used impact echo where a parking garage deck had an overlay on it. You can see the different concrete here. This is the overlay here on top, and this was kind of the structural substrate here underneath. We were getting a pretty strong echo reflection. I want to say it was about 3 inches down or something like that. We took a core, I shoved my phone down inside here and took this picture, so you can see we've got a definite discontinuity right here. And I think the impact echo was, probably within 1 or 2. I think it was within 1 or 2 tenths of an inch at detecting the depth. So it can be pretty effective in the right application. We'll move on to half cell corrosion potential. It's ASTM 870C876, measures the electrical potential within concrete. We know that corrosion is an electrochemical reaction involving the movement of electrons. Again, electrons are negatively charged particles. So the more negative the voltage is within the concrete, or the voltage potential within the concrete, the more negative that voltage potential, we know that there's more electron activity, more electron movement going on, which implies that there's a higher probability of active corrosion, again, because those electrons are moving around. Half cell corrosion potential we typically do on a grid pattern, usually 4 feet or less. 2 feet's probably the more common. It just depends on how coarse or fine you want your data to be. And then we plot equal potential contour lines, and then we can kind of see, just like a topographic map, the high spots and low spots in elevation show up here. High probability and low probability of corrosion is identified. With half cell potential, you have to physically connect to the reinforcing steel. So this image down here in the bottom right, you can see, this is a digital multimeter specific to the application, not just one from Radio Shack, although I guess Radio Shacks don't exist. Anyway, you hook one of these leads up to, physically connect it to the reinforcing steel. The other electrode is hooked to this half cell, which is placed on the surface of the concrete. And then again, you measure the voltage potential. Here we see a negative voltage, and they're almost always negative voltages again. And as the voltage is more negative, it implies that there's more corrosion going on. So here's a map of parking garage deck. We've got girders going across here at line 4, got another girder going across here at line 3, and then we've got these longitudinal panels. Here's a panel, and then we've got these joints from this panel to that panel to that panel, and you can see that right here in these joints is where all of this high, the red is the more negative voltage potential here. Green is good, yellow is kind of marginal, and the red is high negative. So you can see all of these high negative potentials were right where the joints were. Water migrating in there, corroding away, corroding the reinforcement there. It's pretty easy to understand what's going on here. This is a picture of the underside of where we were testing. Not sure that we really needed to do half cell to show us that there was active corrosion going on, because we can see it right here in this photo. But there were some areas that weren't showing active corrosion, visually with this staining that we were able to identify also. So definitely is better than just a visual evaluation. The other thing we can do in the field is figure out the depth of carbonation using phenolphthalein. If you remember from high school chemistry, phenolphthalein is a pH indicator. It turns purple pink at a pH above about 8.3. Kind of depends a little bit on the phenolphthalein solution, and it's colorless below about 8.3. It's colorless to begin with, so it's not like it's pink and it turns colorless. It's colorless and it turns pink. Concrete's got a naturally high pH because of the calcium hydroxide in the hydrated cement. So it's normally going to turn, phenolphthalein is normally going to turn pink. The high alkalinity, that high pH environment, helps to protect the reinforcing steel from corrosion. It offers kind of a passive protective corrosion protection layer. And then as the concrete carbonates, typically from the outer surface in, as the concrete carbonates, it decreases the pH, making it more susceptible to reinforcement corrosion, which is when the phenolphthalein turns colorless. So when that depth of carbonation gets close to your reinforcement depth, that's when there may be a concern. So here's a picture of a core that was extracted out of a parking garage. It was sprayed with phenolphthalein. You can see this is the top of the core here to the left. You can see that there's a little bit of able maybe I don't know, maybe a ½ inch up to a ½ inch in some spots. Pretty. This was on a slab on deck, so the underside wasn't exposed to the atmosphere, which is why we're really not seeing any carbonation here on the underside. But something interesting to point out, we've got this crack right here at the top of the core, and we can see that it's carbonated along the edge of that crack. So if we had if our reinforcement was say about 1 inch down from the surface, that there may be little to no protection at 1 inch because of this crack at this particular location. So these atmospheric gases, you know, they get in even to the little cracks, and we see that all the time when we do petrographic analysis and kind of zoom in on the surface, but we don't always get to see it macroscopically. So that's why I wanted to point it out here in this photo. This is another core that was taken from a parking garage. The top of this core has got microsilica overlay. Microsilica helps to densify the surface to kind of help with chloride penetration. Sprayed it with phenolphthalein immediately after it was extracted, took a picture of it. You can see maybe a little bit of carbonation here at the top surface, but very, very little carbonation. That microsilica overlay is doing a pretty good job. So that brings us to our first review question. Should read true or false. Ground penetrating radar can provide rebar size or diameter. Hopefully everyone's getting their answers in.
Poll is closed. You can continue.
So unfortunately, that's false. GPR cannot give us rebar size. Next question, true or false? Impact echo can provide information on the depth of delamination or flaws. Everyone should be getting their answers in.
You can continue, Steve.
So that's true. Impact echo can give us, does provide us information on depth of delamination or flaws. Question number 3, another true false. Carbonation increases the pH of concrete, offering more protection against reinforcement corrosion. True or false? Everyone should be getting their answers in.
You can continue, Steve.
And that, of course, is false. It does not offer, carbonation does not offer reinforcement protection. All right, now we're going to switch over to some of the laboratory evaluation methods. Surface resistivity, rapid chloride permeability. I put both of these together because the intent, you know, they kind of have the same purpose. One is quantitative measurement of chloride permeability, and the other is a qualitative measurement. The resistivity, surface resistivity, is the qualitative measurement. It's I'm going to say relatively new, maybe 5-7 years. It's got that AASHTO T358. Before that, for a number of years before that, it was a provisional AASHTO method. And then the quantitative measurement of chloride permeability is the ASTM C1202. That's the rapid chloride permeability test. That test has been around for a number of years, but is slowly getting replaced by the surface resistivity test. High resistivity is going to give you a low permeability. The resistivity is done in the kind of the 4-pin Wenner array fashion on a 4-inch diameter sample. The sample size does matter. So some of the numbers that are given for resistance are specific to a 4-inch diameter sample. Permeability, if you're doing the rapid chloride permeability, a high Coulomb number is going to mean that you've got high ion permeability. I think Coulomb is a measurement of charge transmitted over time or something like that. So you know, it's a little bit more of a direct measurement of the ion transport. Moisture surface treatments can have a big influence. Appropriate sample preparation, probably moisture is really the biggest one when doing it in the lab. You know, both of these test methods, the C1202 and T358, there are some conditioning requirements that need to be done in the lab. The surface resistivity can be done in the field, and you can get some good qualitative information with surface resistivity in the field, just with the understanding, as I mentioned, the sample size does matter. So when you're in the field, I mean, you almost have an infinite sample size. You know, and again, you know, surface treatments, moisture. So if you're conditioning the surface properly in the field when doing this test, because you want to get an idea of, you know, is this you know, garage slab, is it suspect to, you know, high chloride permeability? You know, you can use this test to help determine that, but you want to understand that the surface does have an impact. So this is the resistivity method here. This is the 4-pin Wenner array, just kind of a straight line of 4 pins. The outer pins have a current passing through them, and then the inner 2 pins are measuring the voltage from that current. We do the same thing to get soil resistivity in the field. We can get soil resistivity in the lab. Doing this in a box, we can get it in the field, you know, for grounding stations and things like that. So, you know, that 4-pin array has got a lot of applications. But here's kind of a laboratory sample right here. You know, here's the 4-pin array. We tested it, you know, multiple locations. You can see the array back here on the back side also. And then there's this handheld unit that you can take out to the field if you do want to get field measurements. But again, you know, making sure that you know, when you're doing all of your measurements, having the surface moisture consistent at each of the measuring locations is important. For rapid chloride permeability, this is the setup. We're taking also a 4-inch diameter sample of a core or sometimes a cast cylinder if it's new construction. We put it in the test apparatus that has a solution of sodium chloride on one side, so there's your chloride ions, and then a solution of sodium hydroxide on the other side. And then we've got this voltage, negative to positive. Remember, in DC application, you know, that's the direction of current flow from negative to positive. So basically what we're doing is we're kind of forcing these chloride ions through this sample, and then we're measuring how much of the ions pass through. So that's the Coulomb. So if you have a high Coulomb count, you've got a high ion penetration. Low Coulomb count, low penetration. So this slide here is actually from the provisional AASHTO method. I don't think it's in the current AASHTO method, but It really just shows a relationship between surface resistivity and the rapid chloride permeability, and you see we got a pretty good correlation here. We had a couple of outliers here and there, but the correlation's pretty good. The value of this test is it's a lot faster. So the rapid chloride permeability, that test can take up to a couple of days sometimes to perform, but you know, this the surface resistivity is much faster. Here's a table that kind of gives you an idea of chloride ion penetrability, permeability, and these two different test methods. It's an older table that references the old provisional AASHTO method, which is now T2358. But you can see high chloride permeability, penetrability is, you have that when you have a low resistance, low surface resistance, or a high Coulomb count. And just the opposite with low permeability, you know, you get relatively high resistivity and relatively low Coulomb count. You know, again, high resistivity is good for permeability. And again, this is based on a 4x8 cylinder, so these numbers are not valid. These, if you're doing surface resistivity in the field, these numbers may not necessarily be valid in the field. Next ones we'll talk about petrographic analysis and microscopic air void analysis. Each one is unique, but they do pair very well. The petrographic analysis is both a macro and microscopic. Actually, they're both macroscopic and microscopic analysis. The petrographic analysis, we can see signs of internal distress, alkali aggregate reactivity, any kind of, you know, deleterious aggregates, pyrite, pyrrhotite. There was a seminar a couple of weeks ago on pyrite and pyrrhotite and you know, the expansive properties of those. Highly absorptive aggregates might not be good. Friable aggregates might not be good. We can see signs of freeze-thaw distress, sulfate attack, depth of carbonation. We can see really well microscopically. We can get an approximate air void content, but we can't get, you know, it's just done by visual analysis. If you want more in-depth analysis on the air void content for freeze-thaw durability, that's where the ASTM C457 comes in. It gives us different air void parameters. We're looking at it under high magnification. We're doing a bunch of statistical analysis on the different data that we're collecting when we look at it under high magnification. ACI recommendations, air content 5 to 6%, maybe plus or minus 1.5%. That varies with aggregate size. Paste to air ratio recommendation 4 to 10. You don't want a really high paste to air ratio. You don't want a really low one either. Specific surface area recommendations are 600 to 1100 square inches per cubic inch. So that's a ratio of surface area to volume. What that tells us is it gives us an idea of the relative size of the air bubbles. You know, the 600 to 1100 square inches per cubic inch. That's going to give us a relatively small air bubble size. So that's what we're looking for. The last one there, spacing factor, I've got that highlighted because generally that's considered the most important air void parameter, even more important than overall air content. So what that spacing factor is, 0.004 to 0.008 inches, 0.1 to 0.2 millimeters. That's the theoretical distance between air bubbles. So if we've got relatively close air bubbles, you know, the whole idea of putting air in concrete is so that it's so that it holds up to freeze-thaw to stress. You know, it gets wet, the moisture freezes, it expands. We want to give it somewhere. We want to give that somewhere, that moisture, a place to go within the concrete. So if we've got really closely spaced air bubbles, that moisture doesn't have to go very far, even if there's not a whole lot of air in it. So spacing factor is generally considered the most important parameter, and the only way to get spacing factor is by doing this C457. Here's a few images of what the concrete looks like after it's cut and polished. You know, we get a really nice smooth mirror polish on it. This photo up here in the top left corner, you can see the scale bar here, 1 millimeter. So all of these air bubbles, they're relatively small. You know, they're, you know, the largest one there is only about 1 millimeter in size. And you can see how close some of these air bubbles are, you know, so that, you know, 0.1, 0.2 millimeters on the last slide. I mean, you can see that a lot of these air bubbles are within that range. And again, keep in mind, this is a two-dimensional surface. So, you know, 2 millimeters beyond the surface that we're looking at, the air voids are going to look different. They're going to be in different locations. But, you know, the idea with doing all of these measurements and the statistical analysis is to give us an idea that, you know, we're looking at, I don't know if isotropic is the right term, but, you know, throughout the concrete, you know, that we're evaluating enough surface area to make conclusions of what the air void content and what these parameters are within the concrete. I think this picture I just had just to kind of show, you know, how nicely we, you know, it's polished. You know, you can see the light reflecting. You know, we use a light to, you know, help the air void stand out. You know, obviously it's, you know, shadows and things like that. This picture down in the bottom left corner I threw in there because sometimes these air voids get filled in with mineral deposits. You know, there's some mineral deposit, not sure exactly what it is, but some mineral deposit partially filled this air void. So if we've got air voids that are fully filled with mineral deposits, there's no room for that moisture or water to migrate in there as it's expanding. So you could have an apparent air void content that sometimes is less than what you started out with. As strange as that sounds, it's possible. Next, we'll talk about water-soluble chlorides. That's ASTM C1218. This is what's referenced in ACI 318. This table here is 19.3.2.1. I will say that this table is only applicable to new construction, and there are no ACI guidelines for the amount of water-soluble chlorides in existing structures. And ACI, they don't have recommendations because it's just difficult to put a recommendation not knowing, you know, what the structure is, the life cycle, you know, things like that. So really all we have is this is kind of a starting point. What I want to point out here is that these values here, so this is maximum water-soluble chloride ion in concrete reported in percent by mass of cementitious materials. So these values here are, again, percent by mass of cement. So in order to get that, you need to know how much cement is in the concrete. We don't always know that, especially if we don't have any design drawings. You know, we don't have mixed designs. You know, we just don't know a whole lot about the particular mix. And labs like ATL, when they run the test C1218, it's reported The ion content is reported by mass of concrete because you run it on a sample of concrete that includes the cement, the paste, the water, coarse aggregates, fine aggregates, everything. So that value we get is reported by mass of concrete. So this next slide here, it's a little bit busy, but the idea is to show the calculation to go by percent chlorides by mass of concrete, which is usually given. That's the C1218 test that's run. So if we've got percent chlorides by mass of concrete of 0.01%, if we assume the concrete has a unit weight of 145 pounds per cubic foot, multiply that by 27 cubic feet per cubic yard, we get a unit weight of 3915 pounds per cubic yard. If we assume 564 pounds of cement per cubic yard, we'll call that a traditional 6-bag mix. We can figure out what our p-value is to plug into this formula up here. 564 divided by 3915 gives us about 14.4% of cement. So we plug that 14.4% into our formula, and we get 0.069 chlorides by percent of by mass of cement. Chlorides by mass of cement. If this was pre-stressed, this would be no good. I usually use this 0.01 value as kind of a yardstick. Anything more than that, I'm pretty sure is not going to be very good. Less than that is, may be okay. So that 0.01% is a good number to kind of file away in the back of your mind. Acid-soluble chlorides, ASTM C1152, that includes all chlorides in the concrete, even ones that are chemically bound, maybe in aggregates, maybe they're chemically bound in the hydrated cement. They're not soluble, and they are not considered to accelerate the corrosion of reinforcing steel. So most often that water-soluble chloride test is the one that's done. Acid-soluble chlorides is generally accepted to be the total chlorides in concrete, and there is no correlation between acid-soluble and water-soluble chloride methods, other than the acid-soluble is almost always going to be higher than your water-soluble. This photo is just typical sampling methods that we might use to get chlorides. Take a hammer drill, collect the dust. We want to identify, are we getting it from 1 to 2 inches from the surface, 2 to 3 inches from the surface. I always recommend that we get a chloride profile to see what those chloride levels are from the surface down in. Certainly that 2 to 3 inch mark where you're reinforcing steel is pretty important. Knowing what you're sampling. This is a picture of the previous concrete core that had that microsilica overlay. If you're not taking a core, then you might not know that, about 1.5 inches down, that the concrete is changing from a microsilica to regular concrete. That may or may not be important for the chloride test, but just some other, again, we've got this interface here. It's just good to understand what you're sampling. Here we've got a core. It's got some lightweight aggregate in it. Again, importance of sampling. And a lot of times the samples aren't done by ATL staff, non-lab staff. Maybe it's another consultant that goes out. Always want to make sure that we're getting good representative samples, the right sample size, using good sampling methods. Take good field notes. I think I've mentioned that before. Locations, where the samples were taken from. Maybe what depth of the sample. If we're provided chloride samples, powdered chloride samples. Again, just provide as much information to the lab as possible. and it's just good practice to have a chain of custody, so everybody knows what samples we got, where they came from, and the tests that are being performed on them. This last slide here, before we get to our last learning assessment, all of the previous slides and tests that I talked about, those are more for evaluating a structure in place. There's things you can do in the field. There's things you can do in the lab from samples that are brought in from the field. These are just other tests, maybe pre-construction tests that you can do, knowing that your parking garage structure or other exterior structure is going to be subject to de-icing chemicals, freeze thaw, whatever environment. Test your aggregates for alkali silica reactivity. Make sure that they're not going to cause you any problems with the high alkali environment in the concrete. Microscopic air void analysis is always good to have. Do you have those air void parameters that are going to offer you freeze thaw protection? Run some freeze thaw tests. The ASTM C666 kind of evaluates the concrete as a whole, taking into account the water cement ratio, the coarse aggregates, the fine aggregates, everything in there. Is it going to hold up under multiple cycles? The DOT runs kind of a quick test. They've got a 25 cycle test. Again, acid and water soluble chlorides, chloride permeability. You can run the C1202 or another test. It's a European test, NT Build 492, that gives you the chloride migration value, and you can get a chloride migration coefficient that maybe you plug into some life cycle analysis for your concrete. So these are all more preventative tests, some pre-construction evaluations that maybe can be done beforehand. So, okay, we're going to get to our last review questions. True or false? Concrete resistivity can be used to determine freeze thaw durability. We've got a couple more questions, and then we'll get to any questions that you may have that you submitted in the chat.
You can continue, Steve.
Okay, that's false. Resistivity is not related to freeze thaw durability. That's for chloride infiltration or migration. Number 5, true or false? Chlorides that are soluble in water can contribute to reinforcement corrosion. Hopefully everyone gets this one right.
You can continue, Steve.
So that is true. Those water-soluble chlorides can contribute to corrosion. And our last question, this is a multiple choice one. Which air void parameter is considered the most significant indicator of freeze thaw durability in concrete? Specific surface, spacing factor, or paste to air ratio? The specific surface, that's the one that gives us an idea of the size of the air voids, larger versus smaller. Spacing factor is kind of that theoretical distance between air bubbles, air voids, and the paste to air ratio is just a ratio of concrete paste to air.
You can continue.
So spacing factor, that's generally considered the most significant indicator. So that concludes our seminar. I do encourage anybody, if you have any kind of comments, you can send it to that email address, pdhwebinars@atlantictesting.com. Lindsay, if we have any questions that were submitted, we can start to answer some of those. It is 3 o'clock, so we don't have a lot of time, but I'll answer as many as I can.
I'm just giving it a second. There are none in the chat yet. All right, it looks like there are no questions.
Okay, I did such a great job explaining everything. Nobody had any questions. My email address is up there, smore@atlantictesting.com if anyone does have any questions. And our web address is up there also. And I'd like to thank everyone for joining us today.